parametric surfaces and their areas. So now we will learn how to represent a surface in space by a set of parametric equations. So definition, let x, y, and z be functions of u and v that are continuous on a domain R in the UV plane. The set of points x, y, z given by r, vector r of uv equals x, I plus yj plus zk is called the parametric surface. The equations x, where x is a function of u and v, y, where y is a function of u and v, and z, where z is a function of u and v, are the parametric equations of the surface. So first example, identify the surface and find the rectangular equation and then sketch its graph. Given r of uv is equal to 2u cosine v I plus 2u sine v j plus 1/2 u squared k. So x is equal to 2u cosine v, y is equal to 2u sine v, and z is equal to 1/2 u squared. If I use these three equations, if I take x squared plus y squared, that's equal to 4u squared cosine squared v plus 4u squared sine squared v. If I factor out of 4u squared, I'm left with cosine squared v plus sine squared v. That's equal to 1. So I get 4u squared multiplied by 1, or 4u squared. To replace u from z equals 1/2 u squared, this implies that 2z is equal to u squared. So this turns into 4 multiplied by 2z, which is equal to 8z. So my equation is x squared plus y squared is equal to 8z, or if I get z by itself, z is equal to 1/8 multiplied by x squared plus y squared. This is an elliptic paraboloid. So the graph, if that's x, that's y, this is z, that 1/8 will make this graph wider. So there's the elliptic paraboloid. Next example. Find a parametric representation for the surface whose graph is the cone x equals square root of the quantity 16y squared plus z squared. So one way is if I let y is equal to u and z equals v, then r of uv can be written as the square root of 16 u squared plus v squared. Y is u and z is v. The second way is if I let y equal 1 over 4 u cosine v and z is equal to u sine v. Then if I combine these two, the original x equals the square root of 16y squared plus z squared equals, I should get x, and that's my choice to designate y is equal to this and z is equal to this. So 16 stays, y squared is 1 over 16 u squared cosine squared v plus z squared is u squared sine squared v, and all of this is inside a square root. The 16 multiplied by 1/16 will cancel, so I'm left with u squared. Both of these terms have a u squared. If I factor out a u squared, I'm left with cosine squared v plus sine squared v, which is equal to the square root of u squared, which is equal to u, and then u is equal to x. So this technique takes a little more creativity. The first way is the most basic way. So r of uv can be written as x component is u, y component is 1 over 4 u cosine v, and z component is u sine v. Example. Find a vector valued function whose graph is the cylinder 4x squared plus y squared is equal to 16. If I let x equal 2 cosine u, and I'll let y equal 4 sine u. Then 4x squared plus y squared is equal to 4 multiplied by x squared, which is 4 cosine squared u, plus y squared is 16 sine squared u, which if I factor out as 16 from both of those terms, I get cosine squared u plus sine squared u, which is equal to 16 times 1, or 16, which matches the right side of this equation. So r of uv is equal to x is 2 cosine u, y is 4 sine u, and z is free. So I need to add a new variable, so I'll use v. So z can be any value. Next example. Find a parametric representation of the plane that passes through the point 0, -1, 5, and contains the vectors 2, 1, 4 and -3, 2, 5. So a parametric representation would be xyz is equal to the point in the plane. I'll call it ABC plus u multiplied by a vector in the plane. I'll call it v1, v2, v3, plus another vector v, or another parameter v, multiplied by a vector in the plane. I'll call it w1, w2, and w3. So this is a point in the plane. This is a vector in the plane. And this is also a vector in the plane. So the components xyz would be equal to the point 0, -1, 5 plus u, some parameter u, multiplied by the vector 2, 1, 4 plus some other parameter v multiplied by the vector -3, 2, 5. Which means x is equal to 0 plus 2u minus 3v. Y is equal to -1 plus u plus 2v. And then z is equal to 5 plus 4u plus 5v. So R of UV is equal to 2U minus 3V, negative 1 plus U plus 2V, and 5 plus 4U plus 5V. Example, find a parametric representation of the part of the cylinder x squared plus z squared is equal to 9 that lies above the xy plane and between the planes y equals 4 and y equals negative 4. So if I sketch this curve, I get this part of the cylinder that lies above the xy plane and between the planes y equals 4 and negative 4. So this is a y equals negative 4 here. This is a y equals positive 4 here. This point on the x-axis is 3. This point up on the z is 3. This point is negative 3 if I go in the x direction on the negative side. So y is the free variable between negative 4 and positive 4. So I'll say y is free between negative 4 and positive 4, which means v is less than or equal to 4 and greater than or equal to negative 4. If I let x equal 3 cosine u and z is equal to 3 sine u, then let's confirm that we get 9 in the original equation. So x squared plus z squared is equal to 9 cosine squared u. Z squared is 9 sine squared u, which is equal, if I factor out a 9, cosine squared u plus sine squared u, which is equal to 9 times 1, or 9. So my parametric representation is R of uv is equal to x is 3 cosine u, y is v, and then z is 3 sine u. Where u is between 0 and pi, and v is between negative 4 and positive 4. Normal vectors and tangent planes. So definition, the partial derivatives of r of uv equals x in the I direction plus y in the j direction plus z in the k direction with respect to u and phi are defined as the partial derivative of vector r with respect to u is the partial of x with respect to u in the I direction plus the partial of y with respect to u in the j direction plus the partial of z with respect to u in the k direction. And the partial derivative of vector r with respect to v is defined as this. So let x naught, y naught, z naught equal r of u naught, v naught be a point on the parametric surface. Then r of u v naught represents a curve c1 on the surface, and the tangent vector to c1 at the point x naught, y naught, z naught is defined as follows. Analogously, r of u naught v represents a curve c2 on the surface, and the tangent vector to c2 at the point x naught, y naught, z naught is the following. If S is a smooth parametric surface where r of uv is x in the I direction plus y j direction plus z k direction defined over an open region D in the uv plane, let u naught v naught be a point in D. A normal vector at the point x naught, y naught, z naught is equal to r of u naught v naught is given by the following formula. Vector n is the cross product of ru crossed with rv. And this is how you set up the cross product for these two, for those two vectors. So, example. Find an equation of the tangent plane to the surface, r of uv equals u I plus v j plus square root of uv k at the point 1, 1, 1. So at the point 1, 1, 1, this is x, this is y, this is z, which implies if y is equal to 1, that means v is equal to 1. If x is equal to 1, that means u is equal to 1. So this implies that u is equal to 1 and v is equal to 1. So first, if I compute a partial derivative of r with respect to u, I'll do this component-wise. So the derivative of the first component with respect to u is 1. The partial derivative of the second component with respect to u is 0. The partial derivative of this component with respect to u is 1/2. U to the negative 1/2 v to the 1/2. Which is equal to 1, 0, square square root v over 2 square root u. The partial derivative of u with respect to v is equal to, if I take the derivative of this component with respect to v, that's 0. If I take a derivative of this component with respect to v, that's 1. If I take a derivative of the last component with respect to v, that's 1/2 u to the 1/2 v to the negative 1/2, which simplifies to be 0, 1 square root of u over 2 square root v. And now I need to evaluate both of these at the point 1, 1, when u is 1 and v is 1. So Ru at 1, 1 is equal to 1, 0, 1/2 Rv at 1, 1 is 0, 1, 1/2. Now, to find n, I'll take the cross product of Ru crossed with Rv, which is Ijk 1, 0, 1/2 crossed with 0, 1, 1/2. Which is equal to negative 1/2, negative 1/2, 1. Just to clear fractions, I'm going to take this normal vector and multiply it by a factor of negative 2 so I won't have fractions. So this is proportional to the normal vector 1, 1, negative 2. Which means the equation of the tangent plane can be found by taking this component, which is 1 multiplied by x minus the point is 1, since this started at the point 1, 1, 1, plus this component 1 multiplied by y minus the point when y is 1, minus 2 multiplied by z minus the point 1, which is equal to 0. If you simplify this, you'll end up with x plus y minus 2z is equal to 0. Surface area, a theorem. Let S be a smooth parametric surface defined as follows over an open region D in the UV plane. If each point on the surface S corresponds to exactly one point in the domain D, then the surface area of S is given by this formula. The double integral of the norm of RU crossed RV dA over the region D. So example, find the area of the surface over the given region. The part of the paraboloid R of UV equals 2u cosine V in the I direction plus 2u sine V J plus u squared K, where u is between 0 and 2 and V is between 0 and 2 pi. So first, R of UV is given by 2u cosine V, 2u sine V, and u squared. The partial derivative of R with respect to u is equal to 2 cosine V, 2 sine V, and 2u. The partial derivative of R with respect to V is equal to negative 2u sine V, 2u cosine V, and 0. The cross product RU cross RV is equal to 2 cosine V, 2 sine V, 2u, negative 2u sine V, 2u cosine V, and 0. And ijk on top. The cross product, once you compute this and simplify your result, this will equal negative 4 u squared cosine V, negative 4 u squared sine V, and the last component is 4u. Since I will be able to use Pythagorean identity and factor out a 4u from both of the terms that are generated. So the magnitude of the cross product is equal to the square root of the sums of the squares of each of those components. So if I square the first component, this turns into 16 u to the fourth cosine squared V. If I square the second component, that's an additional 16 u to the fourth sine squared V. If I square the last component, I get 16u squared. That's inside the square root. If I simplify this, I can factor out a 16 u to the fourth. If I factor out a 16 u to the fourth, I'm left with cosine squared v plus sine squared v plus 16u squared. Cosine squared v plus sine squared v is equal to 1. So the radicand turns into 16u to the fourth plus 16u squared inside a square root, which if I factor out a 16u squared, I'm left with u squared plus 1 inside the square root, which is equal to 4u multiplied by the square root of u squared plus 1. So once I simplify the magnitude of the cross product, I'll set up the formula to calculate the surface area. So surface area is equal to the double integral of 4u times the square root of u squared plus 1. We'll integrate with respect to v first, and then with respect to u. V goes from 0 to 2 pi, and then u goes from 0 to 2. So to integrate this, I'll do a substitution. Before a substitution, I'm integrating this with respect to v first, so I'm just going to introduce the variable v. So I'm integrating from 0 to 2 of 4u multiplied by the square root of u squared plus 1 multiplied by v, and then v goes from 0 to 2 pi, then I'm integrating with respect to u. So if I plug in 2 pi for v, 0 for v, subtract the two answers, I'm going to get 2 pi as a constant multiple, multiplied by the integral from 0 to 2 of 4u square root of u squared plus 1 du. This is a u substitution. Instead of u, I'll use a different letter. W is equal to u squared plus 1. So dw is 2u du. So u du is 1/2 dw. So this is equal to 2 pi. I'll factor out the 4 in front. U du is 1/2 dw. So multiplied by 1/2. I'll leave the dw inside. This turns into w to the 1/2 power. Bounds of integration. When u is 0, w is 1. When u is 2, w is 5. So this simplifies to be 4 pi multiplied by w to the 3/2 times 2/3. I'm evaluating w at 1 and 5. Which simplifies to be 8 pi over 3 multiplied by 5√5 minus 1. Instead of changing your bounds of integration, you could change back to use after and keep the same bounds of integration, but don't put 0 and 2 on your new bounds for the integral since I'm integrating with respect to w. And since this is surface area, this would be in square units. So then this takes us into the last theorem. If S is a surface with equation z equals f of xy, where xy lies in D and f has continuous partial derivatives, then the formula for the surface area that we just did turns into the double integral over the region D of the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared multiplied by d8. So example, find the area of the surface defined by the part of the cone z equals the square root of x squared plus y squared that lies between the plane y equals x and the cylinder y equals x squared. So first, if I sketch this region, to look at the region D, we'll call this x and this y. So y is equal to x squared is that curve here. Y equals x is this curve here. So here's the region that I'm integrating over. F of xy is the same as z. So f of xy is equal to square root of quantity x squared plus y squared, or x squared plus y squared to the 1/2 power. So surface area is going to be the double integral over the region D, and D is this region here, of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared, the square root multiplied by dA. So for this region, let's do dy dx first. Y goes from this point up. This is y is equal to x squared. This is the line y is equal to x. So the region D, if I choose dy dx first, the lower curve is x squared, the upper curve is x. So I'm integrating from x squared to x of 1 plus the partial derivative of this function with respect to x is going to equal 1/2 multiplied by x squared plus y squared, decrease the power by 1, negative 1/2, and then multiplied by the derivative of the inside portion with respect to x, which is 2x. The 2's cancel, so I'm left with an x over the square root of x squared plus y squared. This quantity is going to get squared, plus the partial of f with respect to y is 1/2 x squared plus y squared to the negative 1/2 multiplied by 2y, which turns into y over the square root of x squared plus y squared. This quantity gets squared. I have to simplify that inside a square root, and I'm integrating with respect to y first, and then with respect to x. So y goes from x squared to x goes from 0 to 1. If I look for the intersection point, this is an x value of 1, where I set x is equal to x squared. So 0 is equal to x squared minus x. If I factor out an x, I'm left with x minus 1. So the 2 points of intersection of those two curves are x equals 0 and x equals 1. So x goes from 0 to 1. So to integrate this, if I square this and square this, and add those two together, I get the integral from 0 to 1, and the integral from x squared to x of 1 plus x squared over x squared plus y squared plus y squared over x squared plus y squared. All of this is inside a square root, and I'm integrating with respect to y and then with respect to x. Both of these have the same denominators, so I can combine those into a single fraction. The integral from 0 to 1, the integral from x squared to x of 1 plus x squared plus y squared over x squared plus y squared inside a square root dy dx. This value is equal to 1. 1 plus 1 is root 2. So if I factor out a root 2, since it's a constant multiple, I'll factor it out in front of the double integral. I'm integrating from 0 to 1, and then from x squared to x of dy dx. Which is equal to the square root multiplied by the integral from 0 to 1. That's y. I'm evaluating y at x squared and x, and I still have to integrate with respect to x. So this is equal to root 2 multiplied by the integral from 0 to 1 of x minus x squared dx, which is equal to root 2 1 1/2 x squared minus 1/3 x cubed. Evaluate this at 0 and 1. I end up with root 2 over 6. And this would be in square units since it's the area of a surface.